To see the current density vector, also called J vector. This represents, in a sense, the flow of charges could be in a wire, for example. So if here we have the wire like this, the flow of charges per unit of some area, cross-sectional area per unit of time is the J vector. So this is like the charge, this charge per area per time. So in some unit of time, could be 1 second. So the units are coulombs per square meter per second. Now, if I want to know how much charge I have in, let's say I have a small surface, infinitesimal surface ds. If I want to know how much charge is flowing through this surface, through, let's say, this surface, then I just multiply the J vector with the ds, because if I multiply this times area, I would get just charge per time. That would be how much charge is flowing per this unit of time in this cross-sectional area. This is true whenever we have the cross-sectional area being perpendicular to the J vector, to the flow of the charges. But if I have that this cross-sectional area is, for example, like this, or this current density vector is this, that is, it is not perpendicular to the surface, then the charges that would be flowing through this cross-sectional area that is not completely it is not perpendicular, let's say it is like this, so it is not perpendicular, so that amount of charges that are flowing per unit of time in that cross-sectional area would not be just J times ds. I would need to take the cosine of the angle between the J vector and the normal vector to the cross-sectional area, or you can think as taking the sine of the angle between the cross-sectional area and the cross-sectional area and the J vector, but we usually think it as with the normal vector. So if the normal vector is parallel to the J vector, then the J vector is perpendicular to the cross-sectional area. So the charges that will be flowing per unit of time in this cross-sectional area, infinitesimal cross-sectional area, is just J times the unit vector. This is the normal unit vector, normal to this cross-sectional area, dot ds. And the amount of charges that are flowing per unit of time, that is dq in dt. This is what we call current, and the units are in coulombs per second, or amperes. So this is current. So we can equate these two, that J n dot ds is equal to dq in dt. Now the charges that would be flowing through this cross-sectional area is the same amount of charges. So here I'm talking about the amount of charges that are flowing. So here I'm just talking about charges, the amount of charges. So what I will get is in coulomb. What I'm talking is something that has coulomb units, because I'm talking about the amount of charges. So the amount of charges that are flowing through this cross-sectional area is the same as the charges that would be contained in a volume, in a cylinder of dimensions ds L, because the charges that are here are the density times the volume, and the volume is ds times L, and this times density. Now L, or distance, is the same as velocity multiplied by time. So I have that Q is equal to density ds, and L is velocity times time. So the current is dq in dt. So if I divide this by dt, actually here is dt because we're talking about the infinitesimal time, I would have that the current is equal to the density times the cross-sectional area, infinitesimal cross-sectional area, times the velocity. Now here I can cancel the ds, and so I have that the current density is the same as the charge density times the velocity of the particles or of the charges. Let's check the units. Here we have meter, we have charges that are coulombs per cubic meter, and here we have meters per second. So the units are again coulombs per square meter per second. These are the units of our current density vector. Alright, the next is, if we have a closed surface, could be a sphere, could be a torus, but not a plane, for example. Let's say this is my torus. If I have some flow of charges that are going out in this flow, because the charge is conservative and there will be no destruction of the charges, and there is flow through this surface, that means that the charge is going from here inside the surface out to outside the surface. So the charges are decreasing. So we have that the current that is in this case would be minus the Q in dt, because the charges are decreasing, so we have a negative sign. And also the current is equal to the flow of the charges, and the flow of charges per unit of time per unit of this area would be the surface. Well, first, here I took a infinitesimal surface, so I will continue with the infinitesimal surface. So it would be just J and ds. If now I want not only the rate of change of the charges per this surface, or the flow of charges flowing through this surface, infinitesimal surface, that is the same, that is current. If I want the total current, so the total current would be the integral of these two things. That is the same. And here we are talking about a surface integral, so we could write just one integral, or we can put two integrals. It doesn't matter, because we know here that because we're putting ds, that means that it is the integration with respect to the surface. And because we're talking about a closed surface, we write it as this. So this is the surface, a closed surface integral of the J vector. Now the charge, we saw that it is density times volume. So actually we have that the Q is equal to the density times a infinitesimal volume. If now I want the total of the charges, it would be the integral from volume A to volume B of the density times dV, and this would be equal to the density times the change volume. So here I could also put it that the total current is equal to minus the volume integral. I could write 3 of these, volume integral of the density dV. This is the charge. Of the derivative of that is the derivative of the charge per time. The charge is density times the change in volume. So the derivative of this with respect to time, and this would be equal to the closed surface integral. Let me write it as this because maybe you will be more familiar with this notation. I don't know. Times the J current density vector dot ds. Now remember that we have one of the fundamental theorem in multivariable calculus is that the closed surface integral of some vector, let's say the vector of the force, for example, dot ds, this is exactly equal, I will put the identity axiom, to this was a surface integral, so sometimes you can write a s here, to the volume integral, that is triple integral, or you can just write one and you put dv, of the divergence of that vector. That is the divergence of this vector, dv. This is with respect to what you're going to take the integration. So now we can write, instead of writing this part, we will write this. So we have that the total current, that is the negative of the volume integral of the derivative of the density times this change of volume in dt. This is the same as the volume integral of the divergence of the, here I'm not talking about force, I'm talking about the j vector, of the j vector dv. Oh, here I forgot to put the dv and here dv. So I undo the integration, and so I have, because if the integral of this is equal to the integral of this, that means that this is equal to this, so I can take out the integral. So I have that the negative of the the negative of the derivative of the density times the volume in dt is equal to the divergence of the j current density, like that. Or you can put it as the rate of, actually here it is, if you take now the derivative, it converts in partial derivative. So you can put this as the negative of the partial derivative of the charge with respect to time is equal to the divergence of the current density vector.